The Urban Challenge. A 60-mile drive through an unfamiliar city full of intersections and stop signs, but without a driver. Researchers at Stanford University and Volkswagen are rising to the challenge. Can a car find its way all by itself and without a driver? The engineers have only a few months to develop brand new technology for the race with driverless cars. Researchers at Volkswagen's Electronics Research Lab near San Francisco are facing the challenge. 50 researchers from 10 countries are working on the automotive electronics of the future.
We'd like to open a window, giving a view into the future, what kind of systems are expected in 10 or 15 or 20 years, and what are the first steps to come into it. And that's the reason why we are here and why we are working so close with Stanford. These experts and our talented people gives us the opportunity to work on these great ideas and to create concrete demonstrators from this region and bring this overseas to real decision.
The Electronics Research Lab is located in Silicon Valley, right next door to Stanford University. Ganymed Stanek and Tim Hilden are engineers at the VW lab. Nearly 2 years before the Urban Challenge, they're researching which maneuvers a driver undertakes unconsciously in city traffic.
Genny puts on the brakes, accelerates, turns on the blinker.
I've got a green light and want to turn left. Now I have to decide if there's enough space for me to turn. It's very hard to estimate. I'm going to try it even though the space is too small, because I assume the other driver will slow down.
There we have a very sporty biker on the road.
You not only have to anticipate what other people are going to do. Once in a while, you don't realize what others have done in time, and then you have to react.
Gurney, tell me what you're thinking right now.
Pretty woman.
Where?
One advantage of a driverless car, it doesn't respond to every stimulus. But that still leaves plenty of challenges for the engineers and software experts.
We can certainly program a couple of important basic driving rules, and we can go a bit further with some frequent special cases. But we discovered so many situations that you never would have anticipated, and programming all of them into the computer is an enormous challenge.
Looking back to October 2005. The same team that is now preparing for the Urban Challenge developed a car that drove 132 miles through the Mojave Desert without a driver. At the Grand Challenge, researchers raised the bar for the current competition.
Ladies and gentlemen, here comes Stanley.
In just under 7 hours, Stanley overtook 23 other cars and rolled past the finish line, winning the world's first race for autonomous vehicles. April 2006, 7 months later. The young team is now considered the favorite. In just a few months, the engineers have to turn a mass-produced vehicle into an autonomous robot on wheels.
So this is the control unit for the steering?
Yeah, and we have to exchange this. And for this we have to take down this entire plate, remove all these screws, take down the wheels.
Wow, there's lots of work to do.
The VW Passat has one big advantage. Nearly all the elements used for controlling the car are already electronic. But some parts, like the power steering unit, do have to be replaced. The new control unit recognizes signals from the computer. Eventually, a central computer will take over the steering as well as the brake booster. When the new unit is assembled and equipped with special electronics, the brakes will operate on their own. In the long run, entering all the commands into a laptop will be too much effort. The engineers have an idea. They start their first unmanned test drive using the joypad from a regular video game. And it works. Now everyone wants a turn. But one problem remains. During the urban challenge, no one is allowed to sit in the back seat.
We can now computer control steering, brake, throttle, turn signals, parking brake. But what's missing is the sensors, of course. In the urban challenge, we need to perceive objects 360 degrees around the car. So we need to have sensors covering all that area.
The ideal partner for the electronics lab is Stanford University, where numerous researchers are working on the software for the driverless car. Sebastian Thrun is the director of the Artificial Intelligence Lab at Stanford. He's considered one of the top researchers in the field of artificial intelligence. Researchers from Stanford and Volkswagen make up the Stanford Racing Team. The team already knows how the car will find its way around.
We'll take laser sensors because they already give us 3D data. Compared to a regular video camera, we only have a 2D picture, but with the laser sensor we already get depth information.
The engineers from the VW lab screw a laser sensor onto the car's roof. Green light for the test drive. Are laser lights really capable of detecting the environment? Can the beams recognize cars and streets? The light detection and ranging system, or LiDAR for short, works like radar. But instead of radio waves, the system uses laser beams. Several units shoot out beams at the speed of light. The pavement and other cars reflect the rays. Thousands of lasers explore the environment within a radius of 300 feet around the car. The reflected light then hits special sensors. The sensors measure the time span between sending and receiving the light signal to the billionth of a second. This allows the LiDAR sensor to determine the distance of an object in the surrounding environment within an accuracy of 5 centimeters. Every second, the lasers are able to measure more than 1 million points. The test shows that LiDAR sensors are able to create a 3-dimensional image of the environment directly in the computer. LiDAR sensors are ideally suited for the urban challenge. But the team wants even more. Mike and Gani install more fittings and stretch a cable through the car. The new sensors are aimed at capturing smaller areas near the car in more detail, like the blind spot at the rear of the vehicle. Just a few months before the big event, the team and the sensors have to pass crucial tests at the site visit. Team leader Sebastian Thrun knows what's at stake.
Today we have to take a series of tests, and if we don't pass, we're out.
At the site visit, staff from the government-run DARPA research agency test all the vehicles signed up for the competition. Only those who pass the tests get to take part. In one decisive test, Junior, the name given to the Passat, has to drive by a parked car while changing lanes. He has to do it alone. The team's software chief, Mike Montemerlo, knows that at this point, everything has to work perfectly.
What's going on there?
So it's passing a car, except I think it got too close to the cones on the outside, and I believe it's stuck.
It's stuck, so...
Yeah.
Oh, good button.
I think they can pause it. I think it's done.
They pause it?
No, it's stuck. And it thinks that it's too close to the cone, and so it won't go.
Okay. So first failure, I guess.
Mm-hmm.
All right. What's the problem?
The position is measured for protocol. Then it's off to the next test. Does Junior recognize who has the right of way? One more mistake could be the end, meaning 1.5 years for nothing. Flawless. DARPA gives Junior another chance to pass the other car. And this time, it works. There are now just a few weeks left before the finale. To get Junior in shape, researchers still need to work on the software. Jesse Levinson is in charge of Junior's localization.
And it's going to look for obstacles in the Velodyne data.
The software now recognizes nearly all external objects, but it needs even more information to find its way around.
Zoom out.
The GPS is very important because it tells us approximately where is our car on the road. So without a GPS, we'd have to try guessing that we are in one of a billion different places. The GPS tells us, okay, we're probably within a couple meters. And then using the sensor data and the digital map file, we can refine our estimate. Instead of being off by a couple meters, we can hopefully be off by just a few centimeters.
But there's not much time to get all systems running together smoothly.
If you're just driving along a road.
It's getting a little bit more tight for us. There's only 2 months left, and there's still a couple of problems we have to resolve. More than we wanted to be at this stage of the game, but we are making progress. We are in the middle of testing right now, and we still find problems with basic things like finding curbs in the sensor data, which we hope to resolve in the next couple of weeks.
So Ganny, Mike, Jesse, Dirk, and all the other members of the Stanford racing team put in a few night shifts in order to install the newest hardware in the car's trunk, to readjust the lasers and solve other problems as well. Finally, the day has arrived. Junior is on the way to San Francisco. In the front seat, safety driver Ganny is steering the car. In the back, Tim starts up the computer and tests the newest software. The laser beams scan the Golden Gate Bridge in a circular motion. The software differentiates between dynamic and static objects. Moving cars are shown in red. Street lamps and the bridge's guardrail are identified as fixed obstacles and are shown here in yellow. The rays even identify the lane markings. That allows Junior to position himself. For safety reasons, Junior isn't driving by himself, but the test shows that both lasers and software are up and running. Sightseeing with more than 1 million laser beams per second. The artificial intelligence in the onboard computer works on 3 levels. At the lowest level, intelligent software converts the laser data into a 3D model. This is the level of perception. The computer then provides the model with a digital map, complete with diagrams of streets, lane markings, and even stop signs. The alignment of laser and GPS data allows Junior to identify his position in the city to within 5 centimeters. That's how he recognizes the exact location of the stop sign at the next intersection, giving the vehicle that stopped first the right of way, in accordance with California traffic rules. In addition, the onboard computer carries out strategic planning. Considering the one-way streets, the computer calculates the quickest route to Lombard Street. Perception, localization, and planning are the 3 levels of Junior's artificial intelligence. And he's clever enough to find his way through the streets of San Francisco. Safety driver Gani takes his hands off the steering wheel and lets Junior take over for just a few moments.
It's a nice feeling. You feel like this is really the start of something. We can use the data we have here to do something meaningful with the car.
The test in San Francisco is a huge success, but the new system isn't meant to replace drivers.
This system can also help to prevent accidents. The car knows what's going on around him on all sides. So if you would be up for doing a mistake, the car could warn you in advance.
In the future, this function of artificial intelligence could become a standard feature in mass-produced cars, helping to prevent accidents or even taking over the wheel during stop-and-go traffic. But until then, Junior has one more obstacle to overcome: the NQE and the finale of the Urban Challenge. October 26, 2007. 35 teams meet in Victorville, California with their robots for the NQE, the national qualifying. Whoever wants to make it to the finale with their robot has to pass several tests here over the next few days. Junior and his engineers are among the contestants.
We feel quite relaxed now, actually. For big things, it's too late, and small things are resolved.
A few hours later, and the testing begins. With the first check, DARPA staff want to ensure that the driverless vehicles can come to a stop at any time. Junior is to be started and stopped via radio signal. But there's a problem. Junior won't start at all. What's wrong? There's not much time to identify the problem.
All right, so you got 2 minutes to,
Is it a software or a hardware problem?
I got it. I get it.
Get it?
Okay.
So come up here and turn the steering wheel for me, please. Okay, that's good. We're getting you. So, okay, let's read. I want to get everybody out of here and let's do it again.
Everybody out of here. Now. Leaving.
Anyone who fails this test can forget about taking part in the rest of the NQE.
Roger. Ready for run, vehicle 3.
There's only one more chance. And he makes it at the last moment. In just a few hours, Junior has to pass the next test. In the meantime, Ganny, Tim, and Mike need to find out what went wrong.
We're getting closer.
Okay, how small is the circle?
About that size.
2 days later, they still haven't identified the problem, but luckily it hasn't happened again. The team members are considering the next test merging into flowing traffic. They show respect for the others. This is also where dreams of taking part in the finale may come to an end.
It is the most difficult test. It's driving in dense traffic, and I've seen some crashes so far already, but I'm optimistic.
Off they go to the hardest test in the national qualifying. Junior is on his way. Will he manage to merge into flowing traffic without taking right-of-way from another car? Perfect. Now the same challenge from the other direction. Junior has to merge again. He's waiting. And waiting. Why isn't he driving? There's no car in sight. Finally, he's made it. Junior makes 11 rounds in 25 minutes without taking right-of-way from another car.
We had to merge into moving traffic, and we did a really awesome job. We're the first team who did it without a mistake, and that's a really great thing.
Yay! That was awesome.
November 3rd, 2007. The finale of the Urban Challenge. 50 cars with drivers are simulating normal traffic in a small town in America. And Junior is joining them. He passed all the NQE tests with flying colors, and he's now one of today's favorites. Go, 10 other driverless cars are creating heavy traffic in the town, which is blocked off to the outside world for security reasons. Junior masters the first intersection. The winner of the Urban Challenge has to drive the 60-mile course as fast as possible without leaving the track and without violating any traffic rules. The robot Skynet and Knight Rider get stuck. And Junior is approaching the intersection. Does he recognize that Knight Rider isn't moving anymore? Or does he think he has to give the robot right-of-way, which would cost him valuable time? After just 10 seconds, Junior has figured it out and is able to continue his mission. Meanwhile, the Carnegie Mellon and Virginia Tech robots have parked perfectly. But robot Terramax has a little trouble finding his parking place. This heavyweight is not the only one experiencing difficulties. During a press conference, team leader Sebastian Thrun hears some news via radio. Ben and Knight Rider almost had a collision, and now they're backing up traffic. Junior is stuck in the middle.
We never know whether a car is permanently disabled or just temporarily disabled. So after a certain time, it just goes and passes everybody. And it's always a dangerous situation, I can tell you. We sweat.
The Ben Franklin racing team is trying to get their robot running again.
So Junior has been sitting there for 5 minutes already. Like, is it losing the race because it's just not moving? Or is it doing the right thing because the other cars will clear up? We don't know. That is the essence of the Darfur Urban Challenge.
The essential feature of the Urban Challenge is that the evaluation criteria are kept secret. That way, teams aren't able to fine-tune their software in accordance with the criteria in advance. The robot who wins should be able to park and turn just as quickly and securely as a human driver, and not just gather points during the race.
How it's going?
It's going very well. Junior just completed the second of 3 missions. Carnegie Mellon and Virginia Tech have also just completed them. It's a very close race, and it's hard to say who's ahead, but it's 3 really good robots.
The 3 favorites, Virginia Tech, Carnegie Mellon, and Junior, all reached the final stage at about the same time. None of these robots has committed any serious traffic violations. At this point, time is of the essence. Who will be the first to make it through the last mission?
Junior, the first clock to receive the finishing checkered flag.
After driving 4 hours and 5 minutes, Junior is the first to pass the finish line. A few minutes later, he's followed by the robot from Carnegie Mellon University, even though he started the race much later than Junior.
It's unbelievable that we actually accomplished this. We're really happy that we reached the finish line. That was our goal. We don't know if we're in first, second, or third place. But that's not the most important thing. It's a huge success for us and for the entire field of research. We're thrilled.
So let's see. Here we go. Who got the million? Junior!
Junior takes second place. And the $2 million check for first place goes to Carnegie Mellon University.
I'm ecstatic. It's fantastic. We are at the very top. It's unbelievable. Again, we are very top. We are number 2 this year, not number 1, but it's supposed to be very close. But more importantly, 6 robots made it home, and a lot of great technology has been showcased. It's a really significant event, I think, in the history of robotics. I'm really excited.
A stunning success for the Stanford racing team. Junior drove nearly 60 miles through a town he'd never seen before. He made no serious mistakes. And he drove almost as perfectly as a human driver. In just 2 years, software experts and engineers have developed brand new technology. Using this technology to create intelligent systems that can help prevent traffic accidents will be their next urban challenge.